Mr. Humbert here. So, power is work over time, and it's defined as the rate of work being performed. If you want that triangle, it is work, power, and time. So you cover up one, the T, I'll get work over power. The P, I'll get work over time, and the W, power, and some time will give is work. It's the rate of energy transfer. The unit of power is the watt. That's all you need to know about that. For the most part, it's a very useful quantity. We use it in electricity. It's used in everything almost in our modern lives, like fridges, toasters, you name it. So for this problem, just a quick example, I have to use something. So what I have to use is the fact that work is, since I have an acceleration here, it says accelerates, and my acceleration is 42.5 minus 0 over 0.06 seconds. I have to use that the change in kinetic energy is the work. And I get this relation from the fact that work is force times distance, and force is mass times acceleration times distance. And acceleration can be solved from the fact that we can use this equation. And we're going to change this delta x, let's change an x to d. And I will solve for a. And a is going to give this change in velocity squared over 2 times, instead of delta x, I'm going to say that this change in x will be distance, which is a very common thing. Most of the time it is. Distance is usually the change in x. Now if I plug in what a is to that a down there, I'm going to get mass times this change in velocity, there's a squared, over 2 times the distance times the distance. That distance is going to cancel, and I get that this is 1/2 m v final squared minus v initial squared. So there's where I get my, and if I put this to both of them, distribute, I'll get 1/2 mv squared minus 1/2 mv squared, or change in kinetic energy. So that's true. Alright, so using that, all that's to say, I can use that relation as work is change in kinetic energy, and then power is work over time. So change in kinetic energy over time is going to be one-half m is 0.14, because kinetic energy is 1/2 mv squared times 42.5 squared, and that's from rest, so the initial energy velocity is 0. And that means that the kinetic energy initial equals 0. So we really just need the final. So once I have that, plug in all those. And this is the top part, it's the kinetic energy. And I need to divide that by the bottom part, 0.06. And once I do that, I will get around 2100 watts. All right. So the next part, say you're given this velocity alongside of it. You could solve for power as work over time times, and from here I'm going to change this work into force times distance after I set it equal to it. And then I want to set that distance equal to the displacement. Force times the displacement time equals the power, and that is equal to force times velocity. So here's another definition we can remember. Power is equal to force times velocity as well. All right. So using that definition, we can solve the next problem. This is our last problem. So say we have this 193 kilogram block. It needs to be raised 7.5 meters from 0 at this constant rate in a time close to 5 seconds. Well, this is going to be of some velocity because v equals change in position over time. That's meters. So that's my velocity value. My force is going to be mass times the acceleration due to gravity, and it's going to be positive because I'm going upward. So my power will be the force times the velocity. So 193 times 9.81 times 7.5 over 5. And I want to find that value to be roughly 2,800 watts. And I'm just kind of giving an approximate answer here. And that's all I have for today.